Doing okay this morning? Any big plans for the break? Studying the whole break. Do y'all have exams after the break as well? A lot of exams? What's worse, this week or after the break? This week is worse. Okay, I'm sorry for that, but I like to have that day when we come back to hand your exams back and sort of go over the final, what you expect. But um, if you guys have your take home, feel free to drop it off. Like if you're done with it, feel free to drop it off to me. If you have it completely done, it's okay. It's not due until Friday morning at the exam, but it could help me get your exams back more expediently. Okay, I'll try to get them back on that Friday. Likely, it's going to be into Thanksgiving break. Like I won't wait until the break's over to get the grades due, but it might not be that Friday either. Um, so I just want to go over the exam today. I think we finished everything for optics. We did the mirrors and the lenses and the two lens systems, but all that you'll see on the exam. The exam is worth 70 points, but it's still a similar length. In fact, I think there were 5 questions on the exam, if I'm not mistaken, 5 or 6, but some of them were pretty short questions, just one step, do a cross product, draw a ray diagram, that sort of thing, that should only take you a couple minutes to do if you know how to do it. So let me sort of summarize what's going to be on the test. We have chapters 7 and 8 and 10. Chapter 7 was on kinematics, rotational kinematics. And so we had kinematics problems, of course. These are problems dealing with theta, omega, and alpha. You have several examples of that in your homework. Make sure that you're up on that. Also, relating linear to angular quantities. You won't have a separate problem on this, but it may become important when you're working through some of the problems that you know, for example, that V is equal to omega R, A is equal to alpha R, S is equal to theta R. We talked about that, how these linear and angular quantities are related, and you'll also see that in the multiple choice. I'd go back over the concept test questions from chapter 7, sort of go through the chapter as well. Finally, we did centripetal forces. Make sure that you're up on that. There were some homework problems in the homework, and then we also worked a problem in class. I forget what, I think it might have been like a roller coaster, this kind of deal, where if you have, say, a cart on top of the roller coaster, what is the centripetal force? What is the normal force? Or we may have been like a Ferris wheel problem. Remember on these, the centripetal acceleration is always towards the center of the circle. So for example, here, if I had a roller coaster and I had a cart going over the roller coaster, I have several forces that are acting on the cart. For example, I have the normal force, I have the weight, and these combined create the centripetal force, but the centripetal acceleration is in which direction here? It's downwards, right? So the centripetal acceleration is always towards the center of the circle. So for example, if I was over here, my centripetal acceleration would be in this direction. So on the left-hand side, my centripetal acceleration is negative. On the right-hand side, the centripetal acceleration is positive in the upward direction. Go back and look at that problem that we did. We did one in class. I don't think there were specific problems in the homework like this, but look at the problem that we did in class and make sure you're up on that. That's it for chapter 7. On chapter 8, which was very similar, and you'll see sort of combinations of these problems, chapter 7 and 8. So you might have a torque problem where I'm also asking you about kinematic stuff. Chapter 8 had a bunch of stuff in it. We'll certainly see a Newton's second law problem. Newton's second law says that torque is equal to I alpha. You need to know how to find the net torque. Be able to find the net torque. Remember, you have a process there where you have to look at the forces that are involved and ask yourself, do they cause clockwise or counterclockwise motion? If they cause clockwise, that's a negative torque. If they cause counterclockwise, that's a positive torque. If you have questions about this, we can go back and look at some questions in the old test or in the homework or whatever. But let me just summarize now. So you'll be able to find the net torque, adding up all the torques. We've done that in the class several times. Being able also to find this moment of inertia. in which case you'll need to think about the situation. What type of shape is this? Are there multiple shapes that I have to consider? Like, do I have a disc and a bar that are coming together that are both rotating, in which case you have to add their moments of inertia? Or maybe I have an object that has a mass located on it, in which case I would have to use the object, the moment of inertia for the object, be it a sphere or a bar or a cylinder or whatever, and then add up that moment of inertia for the other object, whereas it's like a point mass where it would just be mr squared. We did some examples like that where we added up moments of inertia, so go back and look at those. And then you would solve for your angular acceleration, which is our torque over our moments of inertia. And then from there, when you have the angular acceleration, I would expect to see a kinematics type problem, or maybe calculating the energy or calculating the angular momentum. Okay? Look back at the homework. We did several problems like that. Look at old exams. You'll find some examples. But it'll be something along these lines. We also did angular momentum. Primarily that angular momentum is conserved. Li equals Lf. That was this formula, I omega initial is I final, omega final. You could see that both in the multiple choice as well as maybe in a free response. If I change my moment of inertia, that will change the way that I rotate, because this product always remains constant, assuming there are no torques applied, which if we're dealing with an angular momentum problem, there won't be any torques applied. Okay, what else we have in that? We had energy. Nothing terribly complicated with this. Our kinetic energy is 1/2 I omega squared. If I asked you about the energy of something, I'd probably have it wrapped up in another problem, like one of these Newton's second law problems, asking you to tell me what is the energy of this object at a particular time. In which case, you'd have to find the angular velocity and the moment of inertia. I think that's all on chapter 8. Let me take a quick look. Oh, yeah, so you will have to do a cross product too. It's just going to be a problem set aside, but remember to find the cross product, torque is equal to R cross F. Use FOIL, and then you remember that I cross I is equal to 0, J cross J is equal to 0, K cross K is equal to 0, and then we have our I cross J's is equal to K, J cross K is equal to whatever it is. I think it's negative I. Go back and make sure that you know how to find the cross products of our unit vectors and know how to find the cross product of R and F. We did that a couple times in class and in the homework as well. But you will have just sort of a separate problem, nothing attached to it, just what is this torque? This is R, this is F, what is the torque? Okay? Oh, don't forget too that if I give the coordinates for R, so I could tell you that R has a coordinate, say, I don't know, 2, 3, -4 for x, y, and z. That's assuming that it starts from the origin, and then so the moment arm would be 2I plus 3j minus 4k. We've seen that, right? Pretty sure, where we express the vector in this coordinate notation, but I can also write it in IJK notation like this. This is just the coordinates from the origin, and so my moment arm originates at the origin and ends at those coordinates. All right, I think that really is all of chapter 8. Moments of inertia. Be able to rank those moments of inertia, rank the torques like we did in the concept test, Newton's second law, angular momentum. Yeah, that's all of chapter 8. Most of the material that we've covered is on the exam. There's not really anything that's not. And then chapter 9 isn't on this exam. It's only on the take-home, so you won't see any of chapter 9 with the equilibrium problems. And then chapter 10, you'll see 3 things. You're going to see, well, 4 things. Let's say 4. You'll see a mirror problem. You'll see a 2-lens problem. We worked through one last time. There will be no virtual objects. I sort of alluded to the virtual objects, but you won't have to deal with a virtual object in the mirror, in the lens problem. That's where you have a negative P. So it'll be just sort of real objects, a lot like the example that I worked last time, but with different numbers, of course. With the two lens problem, I'll ask you where is the image located and what is the magnification. You look back at the old exams, though, remembering that these are normally this topic I used to cover in 202. So if you want some extra practice problems outside of the homework, you can look back at those exams from 202. This usually comes later in the semester, so look at exams 3 and 4 from 202. But if you can do the one in the homework and you can do the example that we did in class, I think you'll be okay. It'll be a lot like those. All right, so a two lens problem. Also, we'll only use convex lenses for the two lens problem, just like the one that we worked in class. Mirror problem, two lens problem, also a ray diagram for lenses, or for a single lens rather, a ray diagram for a lens. Ray diagram for a lens. I'll give you a lens. I'll show you where the object is. I'll ask you to draw at least two rays. You only need two rays to tell me where the image is. But I'll ask you to draw two rays and then show me where the image is and then describe the image. That is the image real or virtual? Is the image upright or inverted? Is it bigger or smaller than the object? Okay? You should be able to tell that from drawing the ray diagram if it's real or virtual. These are in the homeworks, all the ray tracing diagrams. We did them in class too, but if you can look back at the homework, and so that solution is online. If you forget sort of how to draw those ray diagrams, you can take a look back at them. All right, and then finally, the fourth thing is that in the multiple choice, I have a few questions about just what type of mirrors or lenses are these, what types of images are formed by these different mirrors or lenses. Your ray diagrams will help you think about that, but remember with our mirrors and our lenses, we have four scenarios for the mirrors and four scenarios for the lenses. So think about that. What type of images are formed by what types of mirrors or lenses? We saw some questions like that in the concept test, but questions like, let's say that I have an image that's upright, virtual, and the same size as me. What kind of mirror am I? I'm a flat mirror, right? If it's upright, virtual, and the same size. But if my image is upright, virtual, and smaller, what kind of mirror am I? A convex mirror, right, like a security mirror. So make sure that you know what those mirrors are called and what kind of images they form. Also make sure that you know what type of optical device they are. That is, are they converging or diverging? And remember, our geometry is given by convex or concave, but that's not necessarily our type of device. So converging devices include concave mirrors and convex lenses. They both cause light to converge. And then diverging devices are convex mirrors, like the security mirrors, and concave lenses. I think that's it. Yeah, so that's the test, chapter 7, 8, and 10. Any particular questions y'all want to go over? I'm going to pull up some old exams, but y'all be thinking about particular questions you might want to think about. Students often have trouble with these type problems. Number 6, consider this bar can rotate about points A, B, and C. Which has the greater moment of inertia? Where would it have the greater moment of inertia? About point A, about point B, or about point C? About point A, right. So whenever you're dealing with these, you want to think about where is the most mass located at the biggest radius. And so here in this one's fairly simple, but you can also have 2D objects, like we did one in class with the concept test. But with this one, at point A, I have all this mass out at big radii, but at point C, I have mass only out to half that distance. So it's going to be a lot harder to move an object about point A than it will be to move it about point C, because about point A, it has a bigger moment of inertia. Make sure that you can rank your moments of inertia. Again, we did that in the concept test, but you might want to go back and take a look at that. You might have to calculate the moment of inertia like this for a system of particles. Remember, this is just the sum of mr squared for a system of particles. Need to know all your units. Need to know uh, your moments of inertia. Let me also, while I'm thinking about it, show you the updated equation sheet. I put it on the website this morning. I made two changes. This wasn't on there before. This torque is R cross F. Students often make the mistake of getting your F and R switched up. It is R cross F, not F cross R. And remember, the cross product, if you change the terms, it negates it. So R cross F is equal to the negative of F cross R. And then I also added the magnification, H prime over H. Oh, let's see. I guess that was sort of old notation. If I remember, I'll change this. If you have a question about it, you can ask me. But this is H of the image over H of the object. H prime is often used to be H of the image. And then that's equal to negative Q over P. And then the lens equation and the mirror equation are both the same. 1 over P plus 1 over Q equals 1 over F. Those are really the only equations we have for Chapter 10. But you'll have those. And then I added this as well. You'll have this table, and you'll need to use that table. Okay, I think we worked a similar problem to this, but you want to take a look at this just sort of to jog your memory? Yes, let's take a look at it. You'll have a question that's similar. So I have a hoop that can rotate about its central point. It has a radius of 2 meters and a mass of 30 kilograms is initially at rest. I have a force that acts upon it, and it acts at the point x equals 0, y equals 2. So first I just need to find the torque that's applied to this hoop. So to do that, I would say the torque is R cross F. R is going to be 0I plus 2J. This is a really simple cross product because I only have one term that I'm really concerned about. Crossed with 12I plus 5J. All right, and then I'll do FOIL. I'm going to go ahead and sort of act it out, even though we really only need to multiply this. But FOIL is I cross I, 0 times 12. But remember, I cross I is equal to 0. Inner is J cross I. So that's going to be 24J cross I. What is it? F. Oh, I didn't do outer. That's going to be I cross J, 0 times 5. I'm going to go ahead and write that out just so we can practice doing that. So it's going to be 0 times I cross J, even though this term would go to 0. But let's just practice doing our cross products. And then the last one is 2 times 5, J cross J. But J cross J is equal to 0, so I won't write that at all. So then we need to find the cross products of these. I like to draw my coordinate system. This is my x-axis, that's I. This is my y-axis, that's J. And this is my z-axis, that's K. And then I can think about my right-hand rule. If you just want to memorize these I cross J bits, that's fine. There's really only 3 to memorize: I cross J, J cross K, and K cross I, making sure that you know those. And then the other 3, like J cross I, are just the negative of those. That's fine, but you're going to need to know the right-hand rule for next semester. And so good time to go ahead and master it now. So if I'm doing J cross I let my fingers go in the direction of J. They fold towards I. Or I can think about it in this way, where J is up, I is in that direction, and then my thumb gives the direction of the cross product. My thumb is into the page, right? So J cross I is equal to what? Negative K. You can also remember that I cross J is equal to K, and so J cross I is equal to negative K. So this is negative 24K plus negative, because J cross I is negative K, plus 0 times K, but that term goes away. We can practice that with the I cross J as well. Fingers in the direction of I, they fold towards J. Now my thumb comes out of the page, right? Or index finger, middle finger, my thumb comes out of the page. A couple of different ways you can do that. If you look online, there's other ways to do the right-hand rule, but I'd recommend doing it that way. I think that's easier. All right? You okay with that? I do have to do a cross product. So that's the torque that's applied. See, I think there are other parts to this problem. I'm going to delete this. And what is the kinetic energy of the sphere after 3 seconds? So my torque was 24, had a magnitude, wasn't it 24? Okay, yeah, but it has a magnitude of 24 Newton meters. So I'm not really concerned with the direction of the torque. I just know that it has a magnitude of 24 Newton meters. Um, and then my moment of inertia for a hoop is mr squared. That's on your table. The mass is 30. The radius is 2. It's 30 times 4, 120 kilogram meter squared. That's the moment of inertia. And then I find my alpha is torque over I. That's going to be 24 over 120, which is what, 2 over 10, or zero .2 radians per second squared. And then if I want to know my energy is 1/2 I omega squared. So I have to find omega. What was it, after 3 seconds, I think? Let's just say it's after 3 seconds. Omega is omega naught plus alpha t. It's initially at rest, so omega naught is 0. So this is going to be 0.2 times 3, which is zero .6 radians per second. And then I can plug that in to find my kinetic energy, which is 1/2 of I, which is 120. That's from right here, times 0.6 squared, and then whatever that is the answer. Something similar to that, where you're combining your kinematic stuff with our cross products, with our moments of inertia, sort of all that thrown into a pot. All right. I think there's a similar problem to this, not identical, and there are a whole bunch of different ways you could approach this, but a similar problem I think is worth 10 points on the test. All right. Can I clear this, y'all? All right. Number 14 is good. Have we worked 14 in class? Oh, we did 15. Okay, number 14 is an angular momentum problem. I can tell that it's an angular momentum because there's no mention of forces, and in a conservation of angular momentum problem, you can't have any forces involved, because if you have torques, then the momentum's not conserved. That's similar when we had linear momentum. If you had forces, momentum was not conserved. So we have a guy, he has a moment of inertia of 100 kilograms, and he stands on a rotating platform and is initially at rest. And then he has a 1 kilogram mass, and he swings it around his head in the clockwise direction. So that's going to cause the guy to go in the opposite direction because his initial momentum is equal to 0. Or rather, yeah, his initial momentum has to equal his final momentum. So his initial momentum is equal to his final momentum. His initial momentum is 0, and his final momentum is the momentum of the guy plus the momentum of the rope. And so those two have to be equal but opposite in order to add up to equal 0. So I can say that L of the guy is equal to the negative of L of the rope. The momentum of the guy is the moment of inertia times his angular speed. That's going to equal to the moment of inertia of the rope, or the mass on the rope, times its speed. So I know some of these values. 100 is the moment of inertia of the guy. Omega of the guy is what I'm looking for. And then the moment of inertia of the rope, I have a 1 kilogram mass at 2 meters. So that moment of inertia is going to be mr squared. That's 1 times 2 squared. 1 times 4 is 4. So this is going to be 4 kilogram meter squared times omega. It's going 1.2 revolutions per second in the clockwise direction. So this is going to be negative, and I forgot my negative out here, but then I solve for omega here. So that's 4.8 divided by 100. is 0.048 revolutions per second. And this was clockwise. Notice that this comes out positive, so it's counterclockwise. So the guy, as he sits on this or stands on this rotating platform and he swings this thing around, it causes him to go in the opposite direction. All right. Be careful with your units too on these. In this case, everything was in revolutions per second. And if you're dealing with angular momentum, that's not a big deal because the units all cancel out and you get the units in the appropriate, I keep that revolutions per second. But like in the previous problem where we're doing torques, everything has to go to SI units. So all of your alphas and omegas, they're all going to be in radians per second. And if they're not in radians per second, then you'll need to convert them into radians per second. Okay? In fact, it's always safe to go to SI units. So if you ever see revolutions or degrees per second, it's always safe to convert it to radians per second. Okay? But sometimes it's not safe to not do that. All right. Any particular problems that you want to go over? All right. You will see centripetal force problems. Like I said, everything that we've covered you're going to see. So make sure that you're up on centripetal force problems like this. Um, remember, our centripetal force, Fc, is equal to the mass times the centripetal acceleration. And that centripetal acceleration is equal to v squared over r. Remember also that since v is equal to omega r, that we can write this as m omega squared r. So if you have omega but not v, then you can use this form of that equation. These are identical. They're just substituting v equals omega r in for v. So that's our centripetal force. Here in this case, if our centripetal force, which is provided by the tension, exceeds 200, then it would break. And then to find V, you would just use this and say 200 equals M, which is 20, V squared over R, which is 2. So it's 10, I don't know, whatever. V is the square root of 20. And then if you wanted to convert that into angular speed for this one, then you would say V is equal to omega r and solve for omega, which is V over r. And then that would give you your square root of 20 over 2 in radians per second. What's that? That's square root of 5, I guess. All right. I know this is fast, but just sort of to give you a flavor of everything that's going to be on the exam, you'll see stuff like this. You should certainly go back and review it if it's not clear to you now. Okay, folks? Let's take a little bit of a look at optics. I can clear this away. Again, your optics stuff is going to be in the 202 exam, so you can go ahead and look here. It's going to be sort of in the later 202 exams. Let's look at spring 2015. Oh, wait, no, we didn't do it last semester, so we've had a semester off from doing no optics. So here's some optics stuff. You're not going to see ray diagrams in the multiple choice. You'll see ray diagrams in the free response. It's not worth many points, I think 5 points, but you'll have to draw those ray diagrams. Make sure that you can tell what kind of images form what type of lenses. Images are formed by what type of lenses or mirrors. So, for example, which of the following can make a real inverted image? A real inverted image can only be made by a convex lens. That's a lens that looks like this. It can also be made by a concave mirror. This is a convex lens, but it can also be made by a concave mirror. To really help, you might want to go out and just sort of write down all those concave, convex lenses and mirrors. Well, let's just do it right here, actually, to help you keep them straight. So if I have this could be a nice little study guide. If I have a concave mirror or a convex lens, these are going to produce the same types of images. Or if I have a convex mirror or a concave lens, they produce these types of images. If I'm outside the focal point, these are going to produce a real inverted image. It might either be bigger or smaller, the same size. It sort of depends on where it is. If it's at the focal point, no image at all. If I'm inside the focal point, I'm going to have a virtual upright. In fact, remember, virtual images are always upright because virtual images have a negative image distance. And so the magnification, which is negative Q over P, comes out positive. So virtual images, like in your bathroom mirror, are always upright. Virtual, upright, and bigger image. This is like the shaving mirror. When you get it up close to your face, you look bigger, you're upright, and that's a virtual image. But this one is like the concave mirror when we burn a hole in the paper. That produces a real image because only a real image can actually affect some change, like burning a hole in the paper. And then a convex mirror only produces one type of image, or the concave lens, and that is an image that is virtual, upright, and smaller. So convex mirror and concave lenses only produce this one type of image, no matter where you are. Remember, the focal length on these things is behind the mirror, so it doesn't really talk sense to be at the focal point. You can't be at the focal point for a convex mirror or a concave lens because the focal point is on the opposite side of where the object is. All right. Let's see. You'll have. Sorry, did everybody get that? You need to know what type of lenses and mirrors form what types of images. All right. It'll be on the screencast. I'm recording, so if you want to pick it up there, that's fine too. You will have a two-lens system like this. I'm not going to work through it again, but you can go back and work through some if you like. But remember, the basic idea is that we treat this as a separate problem, find out where the image is, and then this becomes the new object distance P2, and then we treat this as a second problem with P2, find Q2, find M2, and then the total magnification is equal to the product of our two magnifications. This one looks like it might have a virtual object. If you encounter that on the old test, remember, there will be no virtual objects. You have to draw rays and then describe what type of image it is, just like this one. Go back. You'll just have lenses, no mirrors. Make sure that you can draw at least two rays. Remember, you have three rules for drawing rays: parallel to the axis, through the focal point, parallel to the axis, and then through the center of the lens, unrefracted or unbent. Let's go back and look at those ray tracing diagrams. The rules all play out a little bit differently, but once you do it a couple of times, I think you'll be able to do it for the exam. Just going to ask you for two rays, so make sure you can draw two of those. You can draw more if you want. You'll have a mirror problem like this. Not necessarily just like this, but something similar to this. Mirror problem. You'll want to go through and pick out the data that you have. So here it tells me that my object is 4 centimeters high. That's the height of the object is 4. The height of the image is 2. It also says that it produces an upright image. So that tells me that my image is going to be real or virtual if it's upright. It always is going to be virtual, so I'm going to have a negative Q. Here my magnification is HI over HO. So it's going to be 2 over 4. I don't know right off if this is positive or negative, but this image is smaller than the object. So what type of mirror is producing this image? A concave or a convex? This is a convex mirror. This is like my security mirror. It's convex. right? Couple reasons. It has a negative image distance, right? But just because it has a negative image distance doesn't mean that it has to be a convex mirror, because concave mirrors can have virtual images too. But remember, those virtual images are bigger than the actual object. So this is going to be a positive magnification because it's a convex mirror. You'll need to do a little sleuthing in order to figure out what type of mirror it is that I'm dealing with, and knowing what types of images are formed by what types of mirror will really help you with that. So my focal length here, it says is 20 centimeters. But remember, convex mirrors, where the focal length is behind the mirror, have a negative focal length. So be very careful with that, that you're aware of what type of mirror it is that you're dealing with, and whether that mirror has a positive or negative focal length. Because I can almost guarantee you that you'll have a value there that is either positive or negative, but I'm only going to tell you the actual magnitude of the value. And you'll need to figure out by thinking about what type of image is being formed by this device as to whether it's positive or negative. So that's going to be the real tricky part, is the signs on these problems, especially for the mirror problem, that you're aware of what is the sign of the magnification, the image distance, the focal length, all that business. So make sure that you go back and you review what are the signs of the focal lengths, and what does the sign of the image distance and the magnification signify. So let's see, I'm looking for where the object is located. Looks like I'm going to have to do this with a system of equations. I know that 1/2, that's my magnification, is negative q divided by p. And then I also know that 1 over f, which is 1 over negative 20, is 1 over q plus 1 over p. This requires solving a system of equations. I'm looking for where the object is located. That's p. So I'm going to solve this for q. Q is equal to negative p over 2. And then I'll put this in for q over here. And then I can solve for p. That's what I'm looking for. So I have negative 1 over 20 equals negative 2 over p plus 1 over p. I put this negative p over 2 in for q, and then that right here, and then that I inverted it because it was in the denominator. So this is negative 1 over 20 equals negative 1 over p, so p is equal to 20 centimeters. You could see a problem something similar to that. To solve a system of equations, if you've done your homework, you've had a similar problem there as well. Okay, folks, y'all could do that right now if I gave it to you. Make sure you can do it for Friday, okay? Because you'll have to do something similar to that. Not exactly like this, but the same type of problem as this. Clear this, folks? I think that's about it. Let's see. You won't see a one-lens system. As I said, you will see a two-lens system, but you will see a mirror problem as well. All right. As I said, there are 10 multiple choice. They're worth 20 points, so that's 2 points each on those. And then uh, five or six free response, and they're worth a total of 50 points. So they're anywhere from 5 to 10 points each. We'll meet in the auditorium as usual, 7:15. If you want to come, I'll have the exams ready for you. I recommend that you come, just get that extra 15 minutes. And you'll have until 8:30 is what I usually do, right? 8:30. That gives you 5 minutes to get to your next class. Yeah, 8:30. All right, folks. And then you'll be off for break. And then you have your calculus test, I guess. Is it on the same day? Calculus? It is on the same day. I'm sorry for that. It's just sort of that time of the semester. But that's life, right? So we have demands of us. Make sure you bring your take home. All right, folks, anything else? That's all I have, unless you have questions. All right, folks. Well, I'll see you on Friday. I am out of town tomorrow, so if you need to see me, please come see me today. You can shoot me an email. If it's urgent, I might be able to come in Thursday afternoon. But I'm going on a field trip with my daughter, and we won't get back till about 2:30. But I can come in at that time if you need to see me on Thursday afternoon.